So the curves are getting through the intersection between the surface and different planes. If you move the planes around according to the directional derivative, you're getting a lot of the curves on the plane. On the surface. So these curves, you can compute the slope, and this is going to be given by the directional derivative. Okay. Now, do we all know how to compute the directional derivative? Okay. Next, I'm going to rewrite this guy. It is a linear combination. I need your full attention. Not like I don't need your full attention on Monday's class or next week, but today I need some special attention. So I have this linear combination, all right? I have this linear combination, so it is equal to the dot product of two vectors, as I already did. I'm going to call this vector the gradient. Okay, so this vector is going to be called the gradient. And this is already the directional vector. So this is actually equal to the gradient dot product with the directional vector. So now, instead of having two objects in our questions, I have three objects. I have a unit vector in R2, which is indeed a vector. I have a gradient, which is a vector or a scalar. Vector. It has to be a vector to make this dot product value, right? So I have also gradient vector. So this is how you remember it is a vector. You stop calling it a vector. You stop calling it a gradient alone. You call it a gradient vector. Okay. So this is how I remind myself this gradient is indeed a vector. I will just call it a gradient vector. Okay. So now we can simplify our definition and also the formula of computing the directional derivative a bit. Directional derivative of a function with respect to the direction u is equal to this linear combination, but more simply, it is equal to the gradient dot the unit directional vector. So this is a simplified formula of computing the directional derivative. Okay. So the whole thing would be the key right here. Okay. So the directional derivative as our scalar is the dot product between two vectors. One is given by the gradient vector, the other one is given by the directional vector. Okay? So now I want to practice a couple of examples of computing these different objects. And then I will explain more of what these gradient vectors are and how we can extract some more information from the gradient vectors. So let's look at this example. I have fxy is equal to e to minus 3x squared minus y squared. So I want to compute a gradient vector f and also the gradient vector evaluated at 1 and minus 2. Okay? So computing the gradient vector is nothing but computing the partial derivatives, right? Because the only difference between the gradient vector and the partial derivatives is these guys are scalar value functions. You put the x component as f sub x, the y component is f sub y, you're getting your required vector, right? So computing the gradient vector is nothing but computing the partial derivatives. So partial f is equal to x component. What do you have? E to minus 3x squared minus y squared, and then I need to take derivative with respect to x on the x one. So it's minus 4 in place, minus 6x e to minus 3x squared minus y squared. And the y component is the partial derivative with respect to y. So I'm getting a minus 2y e to minus 3x squared minus y squared. And that's it. That's just your gradient vector, right? So computing a gradient vector, you just need to compute the two partial derivatives and combine them into a two vector. And if I evaluate this gradient vector at 1 minus 2, I'm still supposed to have a vector in the end. I just plug in these numbers. X equals 1, y equals minus 2, I'm getting a minus 6 e to minus 3 minus 4 is minus 7. All right? So this plug-in number in the evaluation, pretty easy part. So y is equal to minus 2, so I have a 4 into minus 7. Okay? So this is the gradient vector evaluated at 1 minus 2. So remember, it is always a vector. So gradient vector is indeed a vector. Any questions? So then, instead of using the linear combination over there, I want to use my gradient to evaluate the directional derivative. Okay? Using the dot product between these two vectors. So I have a function f(x) is equal to, let's look at a simpler function. So minus 3xy plus 2y squared. I want to evaluate the directional derivative at this point with the direction in the vector of in the direction of 4, 1. Okay, this is what I want to compute. So I have a polynomial function, pretty easy. I want to compute the directional derivative of this function in the direction of this vector. So usually, if you want to evaluate the directional derivative, you have to have a point. Right? So we have the point already. And also, you have to have a directional vector u over there. Right? But we have to always make sure that u is of unit length. Okay, you have to always make sure it is of unit length. So it is only talking about the direction. It cannot have any information of how long it is. Okay, so we're only talking about in this direction. If I change the independent variables by a bit, how much the dependent variable will change. So this vector, unfortunately, is not a unit yet. All right. So these kind of questions, the very first step, we want to so-called normalize a vector. Have you heard about this terminology before? To normalize basically means I want to divide by its length, so I can make sure it is a unit vector. So u is equal to 4, 1 divided by its length, 4 squared plus 1 squared. So in the end, I'm getting a 4 divided by square root of 17, and 1 divided by square root of 17. If you prefer to rationalize the denominator, this is 4 squared root of 17 over 17. This is square root of 17 over 17. But we don't require to rationalize the fractions all the time, so you can keep it as it is. Okay. So in the very beginning, I have to make sure the directional vector is of unit length. You have to know how to do this, right? You have to do how to do this. So you normalize the vector, I'm getting this, and then I want to use the formula of the gradient dot product with the directional vector right here. Okay. So what I have of the gradient vector is equal to partial derivative with respect to x, when you have minus 1, and the partial derivative with respect to y is minus 3x plus 4y. Okay. So because we're taking the directional derivative of f evaluated at minus 2, you can indeed evaluate the gradient vector right here and then do the dot product. Or you can do the dot product and plug in number in the very end. Okay, so there are two ways of getting the answer here. For instance, we can get the general formula of the directional derivative. Okay, so the directional derivative of the function with respect to this directional vector is going to be equal to minus 3y minus 3x plus 4y dot product with 4 divided by square root of 17, 1 divided by square root of 17. Okay? So it is a dot product between two vectors. So what do we have? So it's going to be minus 12y divided by square root of 17 minus 3x divided by square root of 17 plus 4y divided by square root of 17. Yes? Am I making any mistake? Okay, so I can combine the like terms right here. I'm getting a minus 8y divided by square root of 17 minus 3x divided by square root of 17. Okay? So that's what we have. And in the end, I want to evaluate du f at the point minus 2, 2. So plug in these two numbers. X is equal to minus 2, y is equal to 2. So I have minus 16 divided by square root of 17 minus 2 minus, I got a plus 6 divided by square root of 17. So the final answer is going to be minus 10 divided by square root of 17. Okay? So this is the directional derivative of a function in the direction of 4 divided by 17 and 1 divided by 17 evaluated at the point minus 2, 2. Yep?
I'm kind of not clear. So what is the scalar actually identified, like from the graph, or what is it pretty much?
Okay, so this is what it is. I will draw another picture, and then I can propose a more interesting question. So again, it is a number, so it has to be a slope or a rate of change. It's just about the slope to a tangent line to which curve. So let's say we have a function given by this polynomial, and I'm just saying it is a surface. It's not exactly this surface, but it is a surface in the three-dimensional space. And I have a base point minus 2, 2. So basically it's going to be a point right here. Okay? So minus 2 and 2. Then I can go up and locate the point on the surface. So this is exactly the function value at this point, minus 2 and 2. Right? So from this point, I can move in different directions to create change in my independent variables. Right? And this particular direction will give me where I'm going to change the independent variable. Right? So it is in the direction of a 4, 1. Basically, it's going to be shooting in this direction. Okay? But that direction is not given by a unit vector yet. What I did over there is I normalized the vectors so I can make sure this is a directional vector which is of unit length. Okay? So if I move in this direction by a small amount h, the point corresponding on the surface will be moved by a small amount as well. All right? So originally it is given by f of minus 2 and 2. After you move the independent variables to a new point on the xy plane, you're going to get a new point on the surface which will give you a different function value at this point. Right? So that number, whatever, 10 over 7, the square root of 17, will be the ratio between the change in the dependent variable over change of the independent variable h. And then you take h goes to 0. And a much more direct way to understand this is, as long as I have a direction, I will be able to create a plane which is containing this directional vector and a parallel to z-axis. Right? So I can create a plane which is containing this direction. That will cut through the surface into a curve. All right? So if you have a plane which is parallel to z-axis and containing this vector right here, so you will cut through the surface into a curve. And at this point, there is a tangent line to this curve. And that number is exactly talking the slope of this tangent line. Okay? So in a very, very special case, this plane is going to be containing the x-axis. That's where you get the partial derivative with respect to x. In a very special case where this plane contains the y-axis, you're getting a different curve. The slope of that curve is going to be partial derivative with respect to y. But given any additional other directional vectors, you can create different planes, different curves on the surface, and you're getting different slopes. Okay? Is it clear? Now I can give you a couple of more examples to practice. So let's do one more, and we will propose the question of the day. these are all the required information here. I have a function e2 minus x minus y. I have a point which is given by log 2 and log 3. And I also have a direction 2, 1, which is in the direction of 2, 1. I want to compute dun. And our notation is still the same. I have a direction which is not exactly the directional vector yet. I have a point and I have a function, so I need a formula gradient dot normalize the vector. All right? So the gradient of this function is given by partial derivatives. So it's basically, if this is our function f, so it's going to be fx fy dot u. Okay? So if you don't remember the formula, you can write it in a separate way. So this is going to be the gradient vector given by partial derivatives, dot product with a unit directional vector. So fx, what is it?
E to the negative x and the
Minus e2 minus x minus y, and the y derivative is minus e2 minus x minus y. Okay, and then dot product with normalize the vector. So I have a vector 2, 1. Normalization is going to be 2 over square root of 5. Square root of 5 is exactly its length, all right? And 1 divided by square root of 5. Okay?
Why are you using square root of 5?
Square root of 5 is exactly the length of this vector because it's not a unit length yet. All right? So if I want to make a unit length in the same direction of this vector, I want u to be equal to 2, 1 divided by the length of this vector.
Yeah.
All right? So the length of the vector is square root of 2 squared plus 1 squared. That's where we have a 5 over here. Yep.
Again, how do we know that's not a unit vector already? Two.
Well, the quickest way you can see it, it is a unit vector. Some of the squares have to be the 1 in order to make it a unit. All right, this guy is definitely not a unit. You have a 2, you have a 1, the length is definitely not 1. Right? Or you can see the absolute value of both of these two components have to be less than or equal to 1 in order to make it possible to be unit length. Right? So this one is definitely not unit. Okay? I can give you a couple more examples just to check whether it is unit or not. But right now, let's finish this problem. So I have